So, the next common test which is conducted for bitumen in an oscillatory shear testing is a frequency sweep test. So, frequency, by varying the frequency, it is like we are trying to understand the behavior of bitumen over a wide range of temperature. So, a inverse of frequency is a time. So, if you want to know the behavior of bitumen over a wide time scale, we do this frequency sweep test. So, in this frequency sweep test, we keep a strain amplitude to be constant and vary the frequency. Frequency is generally varied from a high to low value, for especially when you test a bitumen. So, what you do is, in the frequency sweep test, so initially we subject the bitumen to a sinusoidal shearing. If this frequency is, say, time is, say, it is 0.1 second or high frequency, which corresponds to 10 hertz. So, next cycle will be like a less time, say 0.8 seconds, anything 0.8 seconds. So, the other cycle again will take a lesser time, say 0.6 seconds. So, you vary the frequency and give a repeated load applications, repeated oscillatory shearing, keep the strain amplitude constant. So, the strain amplitude here is constant, keep the strain amplitude constant and vary the time of shearing, time of completion of one cycle. So, if you do this frequency sweep, what will be the response of a material? So, as we know that when you do an oscillatory shear testing, we either measure a dynamic modulus and phase angle. We need a minimum two parameters to define. One, it can be a dynamic modulus and a phase angle, or storage modulus and the loss modulus. This storage modulus represents the elastic response and the loss modulus represents the viscous response. So, we need two material functions to define a viscoelastic characteristics property of a material. So, here let us see how storage modulus and the loss modulus varies with frequency. So, let us understand this graph very carefully. We will pick one temperature first, maybe at 30 degrees Celsius. See, you have G prime and G double prime at 30 degrees Celsius. So, 30 degrees Celsius, this value is G prime, elastic modulus, and this is viscous modulus, G double prime. Now, when you look at the low frequency, at lower frequency, G double prime is greater than G prime. So, what does it mean? If G double prime is greater, viscous behavior is dominating the elastic behavior. So, this happens at a lower frequency. As the frequency is increased, you can see a flip over at one specific point. This point we call it as a crossover. So, at crossover point, G double prime is equal to G prime, or otherwise tan delta, which we defined it as a ratio of G double prime by G prime. Since both these are equal, tan delta value is 1 or delta value is 45 degree. So, at this crossover point, delta value is 45. So, after this crossover, you can see a elastic modulus dominating the viscous modulus. So, in this conditions, before crossover, at low frequency, it is viscous modulus dominating the elastic response. After crossover at high frequency, it is a elastic modulus that is dominating the viscous response. So, we call this response at a low frequency as viscoelastic fluid response or a fluid like response, where G double prime is dominating G prime. In case after crossover where viscoelastic solid like response is dominating, or where G prime is greater than G double prime, we call it as viscoelastic solid like response. So, the transition is happening and you can identify a transition, that is, it is one of a method to identify a transition is identify a frequency corresponding to a point where G prime and G double prime is constant or tan delta value is 45. Tan delta value is 1 and delta value is 45. So, this frequency, crossover frequency, in a way will tell you whether the response is when does the bitumen respond to respond as a viscoelastic or fluid like or a solid like. So, now as the temperature varies, say from 30 degree to 25 degree Celsius, this 25 degree Celsius response, you can see that there is an increase in the modulus as the temperature decreases, and you can see that the crossover point, this is a crossover point at 25 degrees Celsius, occurred even at a lower frequency. So, at again lower temperature, still lower temperature at 20 degrees Celsius, again the crossover occurred at still lower frequency. So, the modulus value here G prime and G double prime depends on frequency. Okay, both are dependent on frequency. We can see that as a frequency increases, the modulus value increases. So, as the frequency increases, both this modulus value increases. So, there is a frequency at which both this G prime value and G double prime value is equal, and that frequency is what we call it as a crossover frequency. So, this value G prime and G double prime also depends on temperature. So, you can see a variation of phase angle with respect to frequency. So, tan delta value is also frequency dependent. So, as we said earlier, 0 degree represents an elastic response and 90 degree represents the viscous response, and 45 degree is a point where the transition occurs between viscoelastic solid to fluid, viscoelastic solid to fluid. So, tan 1, this point here. So, you can see a different kind of response when you test it at different temperature over a different range of frequency. So, tan delta again, it depends on frequency and it also depends on temperature. At low frequency, when the response of a material is viscous, delta value is high, delta is high, and it says like viscous behavior dominates, compared to the elastic behavior. So, you know that the frequency, low frequency represents low speed of a vehicle. So, at low speed, rutting, material starts rutting. This is, if you want to relate the speed to the distress of the material. So, rutting is more critical at a lower speed. So, if you want to simulate the rutting behavior, like it is advisable to know the response of a material at a low frequency. So, we pick or select the frequency depending on the our requirement. If you want to characterize it for a rutting response, you characterize at a low frequency, and if you want to characterize at a fatigue cracking response, you do it at for a high speed or a high frequency. So, this is a frequency sweep test experiment, and it is compared with a model. The model used here is a Burgers model. You know the Burgers model relations for a G prime and G double prime. We have already obtained that relations and we have seen that relation in the last lecture. Now, if you see the model prediction, Burgers model prediction, so one is an experimental value data here and the one without fill is a model data. The one with the filled is an experimental data and the without fill here is a model data at different temperature. So, now if you see this is at 20 degrees Celsius, at 20 degrees Celsius. So, the frequency here is from 0 to 15 hertz or all the way even up to 17-18 hertz, and the modulus value was varied from 0 to 6. Now, if you see this a comparison between an experiment and a model, you can see that at 20 degrees Celsius both this G prime and G prime predictions is valid only up to a certain range of frequency. See, that is, the model could predict the experimental data only up to a certain range of frequency, maybe here up to 4 hertz. The experiment was conducted from 0.1 hertz, so from 0.1 hertz to 4 hertz. So, this happened at 20 degrees Celsius. But when you see the same model prediction at higher temperature, 30 and 35 degrees Celsius, so this data corresponds to 35 degrees Celsius and this data corresponds to 30 degrees Celsius. So, at 35 degrees Celsius, the Burgers model could predict the experimental data very well even up to 100 hertz. At 30 degrees Celsius, the data, experimental data and model data matched nearing 40 hertz. Nearing 50 hertz. So, we can see that the model prediction is or a Burgers model could predict the response predict the response of a bitumen within a stipulated frequency range. That range also depends on the temperature. So, we can say that it can predict a response of a bitumen when it exhibits a fluid like behavior. So, if you see here below 50 hertz, you can see a loss modulus or a viscous modulus dominating the storage modulus or an elastic modulus. So, in this range you have a clear good predictions of a model and experimental data. Now, as the frequency increases, when G double prime becomes less than G prime, so there is a deviation between the model and an experiment. In 35 degrees Celsius, we did not see a crossover, so up to even 100 hertz frequency. So, you can see that loss modulus is always higher than a storage modulus at 35 degrees Celsius for this particular type of bitumen, and this bitumen is VG30 bitumen. So, if Burgers model predicted the response even up to 100 hertz frequency. In this case, if you see at 20 degrees Celsius, the crossover occurred at nearing 4 hertz frequency. A Burgers model has a closer predictions of experimental value less than 4 hertz frequency. As the frequency increased, the experimental prediction and the experimental data and the model prediction varied to a larger extent. So, we can tell that the Burgers model could predict the fluid response, or we already know that Burgers model is more a fluid like model, or it predicts a fluid like response of a material. So, the next material response prediction model used here is a Maxwell model, but it is not a one component Maxwell model. It is a Maxwell model with different relaxation mode. So, we used a Maxwell model with a different relaxation mode arranged in series something like this. So, for this model prediction, maybe a Levin relaxation mode is like this. So, you have a Levin component, like this with a eta 1 G1, eta 2 G2, eta 3 G3 and goes like this. So, now if you look into this Maxwell model pins, here we have given a dynamic modulus and phase angle. In last case, we have seen a storage modulus and loss modulus predicted together. In this case, you can see a dynamic modulus and the phase angle prediction together. You can do it in a both the way, but you have to do both the parameters simultaneously. So, now if you do a model predictions for this data, so the data only with the legend gives you the experimental data and the line gives you the predicted value. So, you know that a single element Maxwell model, if you see a single element Maxwell model, we have seen that the storage modulus, loss modulus response for a single element Maxwell model was something like this. Storage modulus increased with the frequency and asymptotically reached a constant value. Loss modulus increased with the frequency and then decreased. This is what we have seen in the last class. So, if you combine both together, storage modulus and loss modulus, the dynamic modulus value as a frequency will show an increase something like this. Now, this is for a Maxwell model with one relaxation mode lambda, where lambda is defined as eta by g, viscosity function by modulus function. Suppose if you have a different relaxation function like lambda 1, lambda 2, lambda 3, etc., where lambda 1 is eta 1 by g, 1 eta 2 by g2, eta 3 by g3, etc., how the response will be, or in otherwise, will the single relaxation modulus or a single relaxation time sufficient enough to predict the response of a bitumen. So, this plot, it shows that the bitumen exhibits a different relaxation function. In this case, it is 11 relaxation functions at this specific temperature. So, this is a master curve data. What is master curve and how to plot this master curve, that we will see it in the few lectures down. So, this is a master curve data at a reference temperature of 65 degree. So, let us assume that this is a data for a bitumen at 65 degree temperature collected over a wide range of frequency. So, you have a dynamic modulus data here and a phase angle data here. So, this is the actual behavior of a bitumen. Actual experimental data here is given in the just with a legend without any line. So, now if you see the actual experimental data varies something like this, but the single relaxation model varies as shown here in this picture. So, if you compare this experimental data and the single relaxation mode data, we are very clear that a single relaxation mode will not predict the complete experimental set of data. So, for this, if we use a Maxwell model with a different relaxation time, okay. So, now you see here the pink line. So, these are with a different single relaxation mode with a different relaxation time, with a different viscosity function by modulus function, eta 1 by g1, eta 2 by g2 and eta 3 by g3. So, you have a 11 relaxation time combined together to predict the response of a bitumen. So, at this temperature for this specific type of a bitumen, which is again a VG30 bitumen at 65 degrees Celsius, a Levin relaxation time or Levin relaxation functions could combine together to predict the dynamic modulus value and the phase angle value. So, you combine a Levin relaxation functions, this pattern. So, you combine it together. So, this is a range of frequency which is predicted for a specific relaxation time. It was combined together to predict a response of a bitumen. So, now these relaxation numbers or the relaxation mode, it depends upon the temperature we are interested in. Okay, it depends upon the type of bitumen, aging conditions and many other factors. So, there is no fixed factor, but here it is clear that bitumen exhibits a more relaxation time, and it's just not a material that has a simple one relaxation mode, it has a many relaxation mode in it. So, if you want to capture a behavior of a bitumen, you can use a generalized Maxwell model. The number of component in this generalized Maxwell model has to be fixed only by trial and error. So, how do you fix this? How do we fix this number of relaxation mode? We have to do only based on the trial and error and see that it fixes to the wide range of frequency here. So, we have seen two model predictions comparisons with an experimental data. One is a Burger's model and other is a Maxwell model, a generalized Maxwell model. So, Burger's model, we have seen that it could predict only in the viscous fluid like response. A generalized Maxwell model can predict the response of a bitumen over a wide range of frequency, but the number of relaxation mode has to be selected based on the temperature, type of bitumen we use and aging characteristics and many other factors. So, let us summarize what we have learnt in two classes. So, oscillatory shearing is nothing but imposing a sinusoidal oscillation on a material. So, by imposing a sinusoidal oscillation, we are controlling either a strain or a stress functions. So, it can be a stress control loading or it can be a strain control loading. So, when the control is in a sinusoidal pattern, we expect the response also to be in a sinusoidal pattern with the same frequency, only then we can call the response of a material to be a linear. So, we call here as a small amplitude oscillatory shear because the response of the material is linear. So, if the material behaves as a viscoelastic material, it exhibits the lag between a stress and strain, and this lag between the stress and strain depends on the frequency and it also depends on the temperature. So, elastic material has a phase angle of 0, viscous material has a phase angle of 90, and viscoelastic material has a phase angle varying between 0 to 90. To define a material functions for an oscillatory shear, we saw storage modulus and the loss modulus, and both the storage modulus and the loss modulus are dependent functions. We can also use a dynamic modulus and a phase angle value for defining a characteristic behavior of the material, or we can use a storage modulus and the loss modulus. And we have seen these modulus functions and the lag functions are a frequency dependent. We have seen few rate type model, especially 3 models, one is a Maxwell model and a Kelvin model and a Burger's model predictions for a linear viscoelastic response. So, and we have also seen an application of this oscillatory shear testing for a bitumen. So, we have seen how to conduct a strain sweep test and identify a linear region for the testing, and after identifying a linear region, keep this amplitude constant and vary the frequency for conducting a frequency sweep test. Frequency sweep test is a common test that we use it for characterizing a bitumen in an oscillatory shear testing. So, in a frequency sweep test, the response of the bitumen, using a frequency sweep test, we can identify whether the response of the bitumen is viscoelastic fluid like or a solid like behavior. And we have seen that the Burger's model predicted a viscoelastic fluid like response of the material, but it is not good in predicting a viscoelastic solid response of a bitumen. A generalized Maxwell model will be able to predict the response of a bitumen over a wide range of temperature, but even then, if a generalized Maxwell model can predict the response, the number of relaxation mode in the model depends on the temperature and depends on the bitumen we use, and it has to be fixed based on a trial and error. We have to do an iteration process and find out what is the number of relaxation mode in it. So, thank you for your time.